12.2 Buoyancy. If you drop a steel marble into a glass of water, it sinks to the bottom. The steel does not float because it has a greater density than the water. And yet, many ships are made of steel. How does a steel ship float when a steel marble sinks? The answer has to do with gravity and weight. Weight and buoyancy. We all tend to use the term weight and mass interchangeably. In science, however, weight and mass are not the same thing. Mass is a fundamental property of matter. Weight is a force caused by Earth's gravity. It is easy to confuse mass and weight because heavy objects, more weight, have lots of mass, and light objects, less weight, have less mass. It is much easier to lift yourself in a swimming pool than to lift yourself on land. That is because the water in the pool exerts an upward force on you that acts in a direction opposite to your weight. Figure 12.9. We call this force buoyancy. Buoyancy is a measure of the upward force that is fluid exerts on an object that is submerged. The strength of the buoyant force on an object in water depends on the volume of the object that is under water. Suppose you have a large beach ball you want to submerge in a pool. As you keep pushing downward on the ball, you notice the buoyant force getting stronger and stronger. The greater the part of the ball you manage to push underwater, the stronger the force trying to push it back up. The strength of the buoyant force is proportional to the volume of the part of the water that is submerged. In the 3rd century BCE, a Greek mathematician named Archimedes realized that the buoyant force is equal to the weight of the fluid displaced by an object. We call this relationship Archimedes' principle. For example, suppose a rock with a volume of 1,000 cubic centimeters is dropped into water, figure 12.10. The rock displaces 1,000 cubic centimeters of water, which has a mass of 1 kilogram. The buoyant force on the rock is the weight of 1 kilogram of water, which is 9.8 newtons. Look at the illustration above. A simple experiment can be done to measure the buoyant force on a rock or any object using a spring scale. Suppose you have a rock with a volume of 1,000 cubic centimeters and a mass of 3 kilograms. In air, the scale shows the rock's weight as 29.4 newtons. The rock is then gradually immersed in a container of water, but not allowed to touch the bottom or sides of the container. As the rock enters the water, the reading on the scale decreases. When the rock is completely submerged, the scale reads 19.6 newtons. Subtracting the two scale readings, 29.4 and 19.6, results in a difference of 9.8 newtons. This is the buoyant force exerted on the rock, and it is the same as the weight of 1,000 cubic centimeters of water the rock displaced. Buoyancy explains why some objects sink and others float. A submerged object floats to the surface if the buoyant force is greater than its weight, figure 12.1. If the buoyant force is less than its weight, then the object sinks. Suppose you place a block of foam in a tub of water. The block sinks partially below the surface, then it floats without sinking any further. The upward buoyant force perfectly balances the downward force of gravity, the block's weight. But how does the buoyant force know how strong it needs to be to balance the weight? You can see the answer to this question on the illustration above. If a foam block and a wood block of the same size are both floating, the wood block sinks farther into the water. The wood has a greater density, so the wood block weighs more. A greater buoyant force is needed to balance the wood block's weight, so the block is displaced more water. The foam block has to sink slightly more to displace water with a weight equal to the block's weight. A floating object displaces just enough water to make the buoyant force equal to the object's weight. If you know an object's density, you can immediately predict whether it will sink or float without measuring its weight. An object sinks if its density is greater than that of the liquid it is submerged into. It floats if its density is less than that of the liquid. Do you see why the picture dropping two balls into a pool of water? The balls have the same size and volume but have different densities. The steel ball has a density of 7.8 grams per milliliter, which is greater than the density of water, 1.0 grams per milliliter. The wood ball has a density of 0.75 grams per milliliter, which is less than the density of water. When they are completely underwater, both balls have the same buoyant force because they displace the same volume of water. However, the steel ball has more weight since it is a higher density. The steel ball sinks because steel's higher density makes the ball heavier than the volume of the water. The wood ball floats because the wood's lower density makes the wood ball lighter than the same volume of displaced water. If you place a solid chunk of steel in water, it immediately sinks because the density of steel, 7.8 grams per centimeter cubed, is greater than the density of water, 1 gram per centimeter cubed. So how is that thousands of huge ships made of steel are floating around the world? The answer is that the average density determines whether an object sinks or floats. To make steel float, you have to reduce the average density somehow. Making the steel hollow does exactly that. Making a boat hollow expands its volume a tremendous amount without changing its mass. Steel is so strong that it is quite easy to reduce the average density of a boat to 10% of the density of water by making the shell of the boat relatively thin. Ah, you say, but that is an empty ship. True, so the density of a new ship must be designed to be under 1 gram per centimeter cubed to allow for cargo. When objects are placed in a boat, the boat's average density increases. The boat must sink deeper to displace more water and increase the buoyant force, figure 12.3. If you have seen a loaded cargo ship, you may have noticed that it sat lower in the water than an unloaded ship nearby. In fact, the limit to how much a ship can carry is set by how low in the water the ship can get before rough seas cause waves to break over the sides of the ship. Take a moment and answer these questions.